Okay, thank you. Thanks, Ayan, for the invitation to give a talk in this nice workshop. So I'm going to talk about, I think mainly about early time dynamics, and I will also briefly talk about jet quenching. And so this talk is more or less like the expansion of my hard probe talk. So I'm really happy to give a talk in this longer time window, then we can discuss more details. And I want to say more actually. So as all of you know that in our fields, there are two main research directions. One is about jet quenching or hard probes. The other is about bulk matter. Actually, I mean, if we look at the QCD factorization, I mean, in proton-proton collision, actually what actually distinguish different modes in QCD actually is the virtuality. It's not like what we are doing here by separate these two entities by introducing some cutoff, right? So that's basically what we are doing. But in this approach, of course, I mean, if we really want to have a unified framework for the hard process, so we need to decide where we put in this cutoff and how we can really get rid of this cutoff dependence. So this issue actually more or less motivates my talk. And of course, I have done some jet quenching before, but now I'm also doing some bulk matter. So one motivation for me to do bulk is, of course, just let's see how we can do the jet quenching in a time-dependent bulk matter. So as I just briefly mentioned, so in proton-proton collisions, actually QCD factorization plays a central role. So in our fields, actually it's a working assumption, but I think there should be more, much more should be done. And here I just want to give you my view about it. So some topic I have been working on, so I will not report in this workshop, but I just want to give you an overview about what we want to accomplish for the hard process in nucleus collision, maybe also in proton-proton collision, just see how we can really match the calculation in traditional proton-proton collision with our fields. Anyhow, so if we really want to do some calculation from Feynman diagram from QCD, so of course, so we have to first do the power counting. And for example, here I just show you one diagram. So this is one of them we need to consider here, just for a correlation between a jet and an electroweak boson. And but as I mentioned, right, so actually, if we look at the QCD calculation, well, we are also doing QCD, but I mean the productive QCD calculation in proton-proton collisions actually, so they separate modes in virtualities. So this just means if we really want to bridge the calculation in proton-proton collision and the nucleus collision, we need to find a unified way to describe both. Now, of course, QCD factorization is kind of underlying assumption of all the calculation in jet quenching. But of course, there's more discussions recently, so we need to, I mean, if we really want to, from QCD, do the power counting, of course, we need to be careful whether we have this simple form or not. I mean, actually, even in proton-proton collisions, actually, the proof of factorization actually is really, in most cases, are really difficult. So, but I mean, here I only, my discussion will focus on this part, just the more or less like a traditional thing if I talk about jet quenching, but I mostly talk about the bulk, of course. So we want to have, at least we know how to do the power counting, even if we cannot really do the exact calculation. We need some underlying assumption about picture, right? So here I just take the Bjorken picture. So let's in nowadays, so we know a lot about like color condensate. So I think for the underlying picture is really similar. So this picture can go back to Bjorken. I mean, so it's basically just if you imagine either proton or nucleus as a bound state of valence quarks, then what happens is if you collect two objects, so the valence quark will pass through each other mostly. So because they carry the baryon number, actually, so they will carry away the baryon number from the mid rapidity. And what we measured actually is so-called wave parton. So here, so I just check some experimental papers, see what is consistent with this picture, for example. So this is measurement actually from RHIC, actually a long time ago. So if you look at the high energy collisions at RHIC, you will see, so this is the number of net protons. I think it means the number of protons minus antiprotons. Roughly, it gives you some idea about the baryon number. So at the mid rapidity, actually, you will see the drop of this number with the increase of energy. Then, I mean, it is kind of consistent with this like a parton model or perplexity picture. Of course, here there are some issues. So actually in Bjorken's picture originally, so they just assume those gluons carrying an energy of order lambda QCD. So it basically it means non-perturbative. Now, of course, I mean, nowadays we are talking about CGC, so it just means those solved gluons will generate some dynamic perturbative scale called saturation momentum. So here, there's one important, I think in most calculation in our field, so there's an important assumption or just the working assumption is called longitudinal boost invariance. So in all my talk, so I will also assume this. But I mean, this longitudinal boost invariance can be easily understood from this simple picture. So because at high energies, the solved gluon radiation is independent of the energies of the incoming protons. So this just means if you boost a little bit, your result is always the same. Of course, I mean, for this tree level, then of course, if you do the small x evolution, you will get some dependence of the central energy. You will have some dependence of the rapidity at the end. But I mean, I also checked the experimental paper. So I think it's a little bit confusing for me. At least there is, I think for the previous paper, some CGC paper fits very well, but somehow for recent Alice paper, so let's the charge number density of particles in the rapidity space, the rapidity, not the pseudo rapidity space. So it seems the longitudinal boost invariance may not so be good, but I mean, there's a lot of non-perturbative effects one need to consider if one really want to feed the data. And anyway, I just try to see how this picture may be proved or disproved by experimental facts. But I mean, as I mentioned, so if you want to really do some perturbative calculation in QCD, so you need some hard scales, which should be larger than lambda QCD. So in this bottom picture, so it will generate, because of the saturation, parton saturation, it will generate a hard scale QS. So if QS larger, if it's much larger than lambda QCD, of course, it will be nice. But at least at RHIC and especially LHC energy, so QS larger than lambda QCD. So anyway, so as I mentioned, so we need some picture, initial picture. Then if we accept this picture, one can do the power counting. And then we know if we know the density of these particles and also the coupling, of course, one can do the power counting. Then one has an idea, so which diagram we need to consider for observables. Then, so the first part of my talk will be about large system, so which is more or less, mostly is just review, and it will relate to my discussion in the small systems. But I mean, it's most part is review actually. So as I just mentioned, so if you accept this parton picture or so-called CGC picture, then in that case, so all these valence quarks or large X partons will be taken as classical color source. Then, I mean, if your number density of large X, if your number density is large in a large nuclei, so you need to do some, you need to resum certain type of diagrams. So at an earlier time, so you actually only need to resum those tree-level diagrams. So it's just classical diagrams. So it's identical to solving classical Young-Mills equations at leading order. Then in this classical picture, actually one can show that, well, I think this is mostly parametric based on physical intuitions. So at top of order 1 QS, so one can talk about the virtualities of these weak partons. So it will become smaller than QS. So one can roughly say, okay, it's go on mass shell. And in this case, actually, one can do some calculation in this classical picture, classical picture. So one find the number densities will go to like 1 alpha S. So it's really large densities, but at top of order QS, 1 all QS, actually the number density starts to become smaller than 1 alpha S. Then in this case, if you do the power counting for diagrams, then you do some approximation for those diagrams. Actually, those diagrams may reduce to Boltzmann equations. So in this case, one may use the kinetic theory to discuss, but of course, in order to do the real derivation, one needs to assume, to make some assumptions. But I mean, if one take this kinetic theory picture, so one actually has this so-called the bottom-up thermalization. So basically, there are 3 stages in this scenario. So at the beginning, it's quite surprising. And then there are some issues about the stability or something, but nowadays it seems its stability is not so important. So it seems this bottom-up is more attractive somehow. Anyway, so that's why I'm focusing on this bottom-up. So the first stage, so because here I tell you the number densities of these partons, actually the phase space distribution also goes like 1 alpha S. Then, so the first stage actually, so for this, here the V parton is called hard partons now because the QS is the hardest scale for this bulk matter issue. Then the first stage actually, the expansion actually is more important because it's longitudinal Bose invariance. Actually, at an earlier time, actually the system expands very rapidly. Then at this stage, actually the expansion dominates, and one can estimate the jet Quenching parameter. So actually, mainly from the so-called hard gluons. The hard gluons will scatter with each other. They will generate some soft gluons, but those soft gluons do not play an important role at all. So one can neglect them at the first stage. Then if one estimate your head, one can use this formula parametrically. I mean, for small enough coupling, so this will give you the leading effects. Of course, one does not know the exact coefficient. Then from this, one can get estimate the momentum of each partons in the system, from which actually one can estimate the pressure. So actually, as I mentioned, because the expansion dominates, actually you have at the mean rapidity, all the partons will rapidly go away from mean rapidity unless PZ equals 0. But because there are some scatterings between partons, so they will generate some small PZ. PZ is just the longitudinal momentum from which one can estimate the pressure and isotropy when get this kind of behavior. So then there are some classical field simulation by Heidelberg group. So they confirm this behavior I will tell you later. Then in stage 2, so basically the expansion kind of countervails the interactions. So in the sense that, I mean, the soft gluons, still not so important, but it will contribute the by screening effect, and also the base space distribution hard gluons become smaller than 1, so one can estimate the Q hat, the jet quenching parameter, by this formula, and from this one can again calculate the longitudinal momentum of the partons in the system, and such that estimate the pressure, the ratio between PL and PT, so it will get a constant of order of S. Then, so what happens is if you compare the time tau, because in these longitudinal Bose invariant systems, so the typical time for all the quantities in this system to modify significantly is about their tau. So then you have to compare this tau to the thermalization time of your system. Actually, you will find only at the end of the stage 2, actually this 2 time scale is comparable. It just only at this moment, actually the soft gluons may have enough time to establish thermal equilibrium. Then actually this brings us to stage 3. So it basically, those soft gluons can form a QGP, and then the hard gluons will travel in this QGP and lose energy, heat up the temperature of these systems. And when all those hard gluons disappeared, lose all its energies in these systems, then so that's how the bottom-up thermalization ends. So that's as I mentioned. So if actually you can just neglect all the stage 1, stage 2, so you can just start from stage 3, then you take it as jet quenching problem. So you will get this magical time scale for bottom up. So yeah, I don't want to repeat everything, but the thing taken into mind is just jet quenching problem. Then actually your typical energy loss goes like RHIC squared times Q hat tau squared. Tau squared is more or less like the length, the path length, but in this case it's just the time. So this also tells us the connections between this bottom-up thermalization and the jet quenching phenomenon. Anyway, so here I just add all the number in the previous slides here. So the PLOPT, first it will decrease with time because the expansion is more important than scheduling. Then in stage 2, you get some level off. Then at the end, it's called bottom up because the hard gluons will heat up the QGP. Then at the end, actually the temperature in the system will become larger until it's reached some maximum. And as a result, actually you have some isotropization in your PLOPT. Then of course, I mean, all these calculations for us that mentioned, first is worse in small coupling. Second, so there's based on a lot of physical intuitions. For example, like the kinetic theory. So based on a lot of pictures, or at least the system close to thermal equilibrium. So there are many things one may check starting from the Bjorken picture. For example, I mean here in those papers, they just actually just do the coupling expansion, do calculations, and one can calculate the energy density. What they find is actually energy density goes like 1 tau. So this is consistent with the free streaming in kinetic theory. Then, I mean, with Uri, I also calculated actually the 2-point correlation function. Then if you make some approximation for these functions, actually it will proportional to the classical, quasi-classical phase-space distribution function of gluons. So I calculate this one, then if we take a tau go to infinite limit, it's indeed this quantity is proportional to delta p squared. So let's just say, actually in this limit, all the gluons are going much short. Then you can take this as a classical, quasi-classical gluon distribution functions in kinetic theory, but it's not quite. So let me say what I mean. So in this free streaming case, so it does because this piece actually is the same as the free streaming solution in kinetic theory. But I mean, we had to go further. So we just say, okay, so first, I mean, in QCD, it's really, there are many diagrams involved. So we know which diagrams we need to consider in order to, if we make some approximation to get Boltzmann equation. Then we just took those diagrams. If we make the approximation needed, then we can get something similar to kinetic theory. But that's not really QCD calculation. So what I mean is, so the approximation needed is first, we have diagram like this one. Then if you have diagram like this one, you need to make approximations to replace this vertex by an unsolved results like this one. So this, of course, only works in the limit toggle to infinity limit. Then the other one, of course, for this diagram, for this vertex, we need to do the same thing. This is prerequisite. It's not sufficient condition, but it's required to derive, get the same results in kinetic theory in coupling expansion. But I think the surprising part is, I mean, in QCD, because there are so many diagrams, we didn't do the exact calculation. But if we make the correct, why not correct? If we want, because we want to get kinetic theory results, then we make some approximation. In some cases, we can get kinetic theory, but let's just assumptions in a sense. Then we did some exact calculation in QCD, in lambda 5 theory. So basically, it's the same diagrams, but it's much simpler. So because we only do lambda 5. So we get the results actually is really different from kinetic theory. So I think it's quite surprising. You just say, so the QCD, no, the quantum field theory obviously has more features than kinetic theory. So here, I mean, so in principle, one can explore more. And I mean, there's a way to do the calculation. The calculation is really complicated, then it looks different from the kinetic theory, at least in this toggle to infinity limit. So anyway, that's something I am still thinking about. I mean, why this happens. But obviously QCD, I mean, quantum field theory is more richer than kinetic theory, that's for sure. And kinetic theory can be taken as an approximation to quantum field theory, of course. And anyway, as I already mentioned, in stage 1, actually, because the gluon number density is still much larger than 1. So in principle, one can use classical simulation. So there's nice calculation, detailed numerical calculation in classical statistical approach, and they agree with bottom up. Then like Legacy and Ayan, so they have some detailed calculation in kinetic theory. So in the really weakly coupled limits, they confirms the bottom up. Then I mean, there are also, of course, a lot of recent activities. So one of those is just by matching all the calculations in different stage, because there are, say, 3 stages. In first stage, I mean, if one do the power counting, in principle, the classical simulation and the kinetic theory are both valid. So in principle, one do the research there based on this power counting. Then, of course, at the late stage, you can match to the hydro, etc. But I think for the practical way, so that's maybe the most practical way. But if you want to do the field theory calculation, as I already mentioned, so the diagrams are there. It's just how one can evaluate all those diagrams. Then, of course, in the classical statistical approximation, actually, one can include some quantum fluctuations at the initial time. Then actually, if you look at the thermal fixed point, you can get one more terms right if you do the if you do small p, small momentum expansion. So in that case, there's simulation by Thomas and Francois. So they found some rapid fast isotropization in this PRO-PT, but of course one has to make sure how to deal with the cutoff dependence, the non-renormalizability. So I have some paper with them discussing about this cutoff dependence issue. So let's what I want to talk about the large systems for the bulk medical part, but as I already briefly mentioned, because in this bottom up, one can use the language of jet quenching parameter Q hat, right? Then, so actually the connection between jet quenching and the bottom up thermalization is almost identical. So here, if you have really hard jets, actually your energy loss is identical to the hard gluons in the bulk matter. So in this case, at the end of the bottom-up thermalization, the hard jets will suffer an energy loss of order QS, which is a couple of GeV. Then of course, at the end, you will like hydrodynamic evolution. You can do some modeling about how the energy loss calculate. Then, so here, of course, there are also some detailed calculations. For example, in these papers, so they can, if it's one-dimensional expansion, one can do the energy loss problem analytically, actually. So, but of course, in later times, so we have like a three-dimensional expansion, right? In that case, there's no calculation in done. Actually, that's one reason why I'm studying this this bulk matter issue. So there are also some higher order calculations in the one-dimensional expansion, longitudinal expanding systems. So here, one exercise I have done is with Edmund and Peter. So here we just basically repeated the calculation in static medium, and it's not surprising, but I mean it's fine to see by exact calculation is actually the Q hat looks. I mean the radiative corrections to Q hat, it looks exactly like a static media with the path length replaced by tau. So this is exact results for of course for leading log. And this also tells us the typical time scale for the expansion in this one-dimensional system is about tau. Then of course there are also some recent calculation by Zakharov, so they try to get all the terms right there. So for the rest part, I will talk about the small systems. Sorry. So here, I mean, so there's some trivial statement I would like to start. So first, of course, I mean, QCD contains the hydrodynamic equations of hydrodynamics. So here I mean hydrodynamic poles in the correlation function of the energy moment tensor. But actually, quantum field theory goes beyond hydrodynamics. I mean, different quantum field theory, they have different non-hydrodynamic structures. So here, I just show you the poles of these correlation functions in ADS-CFT. So you have hydrodynamic poles, but you have some other poles in this theory. But in QGP, actually, it really depends on the coupling. So we have to figure out what's down here for the non-hydrodynamic part. Of course, for hydrodynamic part, so it also has the hydrodynamic poles. Then here, so sometimes I call hydro. So when I say hydro, I mean just the contribution correspond to the hydrodynamic pole in whatever theory. Then, of course, I mean, if one use hydrodynamic models to fit the data, then one has to be careful to conclude about the hydrodynamics. So you have like hydrodynamic equations, but it's but those equations not only contains the contribution from like hydrodynamic poles, but also has some non-hydrodynamic, which is needed for the consistency of the theory, but it does not correspond to anything in that underlying quantum field theory. So in order to make sure the hydrodynamic models, in the calculation hydrodynamic models, if you can fit data, but you cannot necessarily conclude that hydrodynamic works, because you have to make sure the contribution from this hydrodynamic pole dominates. So here, of course, one naive, well, not naive, just one criteria we brought up in this paper is just, we call it Q. It's basically just the relative difference between the contribution from that hydrodynamic pole and the actual the T mu in your theory. It may be in your quantum hydrodynamic models, it may be in kinetic theory, maybe it's in quantum field theory. But I mean, if this quantity is small enough, you may say, okay, hydrodynamic modes dominate, then the hydrodynamic calculation really valid. Anyway, so here, I mean, in the rest part, I will use a simple theory just to illustrate what I just said here. So for example, I mean, in the ethereal stood hydrodynamic equations, actually there's the non-hydrodynamic part actually correspond to another pole. So while that's the ethereal stood equations, then, but in other theories, as I mentioned, this part will be different. So actually the studying of small systems actually help us to understand what's there if the hydrodynamic contribution does not dominant. So here I only use a simple kinetic theory. So actually why it's interesting, because compared to this ethereal stood correlation functions, you will see the only difference is replace this pole by a branch cut correspond to the free streaming particles. So, but at least in the theory is consistent. If this part is dominant, in the theory is correct contribution, but in hydrodynamic, in this ethereal stood hydrodynamics, if your contribution is important, I mean, the non-hydrodynamic contribution is important, you shouldn't trust this calculation. Anyway, because it does not correspond to the underlying theory. So this equation has been used before, I mean, by Bain. Then here, actually, in the confinement limit, one can really argue there's just one parameter. So basically, it just corresponds to the size R of the system divided by meter per path. Then, of course, one can calculate, I mean, as I mentioned, so you have this non-hydrodynamic structure for both theory, but if you really want to compare it to theory, so you need to calculate the transport coefficient from this kinetic theory for these hydrodynamic equations. So that's the relation between transport coefficient and this coupling of this system. Then, I mean, so we need to understand the non-hydrodynamic modes. There are two ways, right? One is the jet quenching. It's obviously non-hydrodynamic. It's particle-like. The other one is just go to the small systems. So the argument, of course, is just you have two contributions, one from the hydrodynamic pole, the other one from non-hydrodynamic modes. But if you go to small systems, actually this term will surprise. Then if you go to, in experiments, if you go to small systems, actually you can just study more non-hydrodynamic structures in these correlation functions. So the first thing we do is, okay, we just want to see how the particle-like picture or non-hydrodynamic picture contributes to flow. So here, actually, we did some analytical calculation in this theory. So we find some interesting picture. So here, we actually also just compare to other kinetic theory calculations. So it's kind of universal for this picture. So basically, if you have some initial anisotropy in coordinate space, so if you have this elongated distribution and initial time for your initial partons, if you assume the momentum is isotropic in space, then actually at R of order tau, so the particles separated by 2r will encounter at the center. So actually, this gives the dominant contribution for flow when those particles encountered in the center. I mean, if there's no interactions, they will pass through each other, and so you don't have any flow. But if they encounter, they scatter, they will change their directions. Actually, it will generate more particles which moving along the px direction in momentum space. So that's how the actual single scattering can contribute to flow. So it's kind of in it's different from the typical hydrodynamic pictures. Then I mean, as I mentioned, so we can do almost analytical calculation in this simple theory for the V2, for the older VNs actually in principle. Then I mean, we also do some the calculations for the linear response theory actually in kinetic theory. Here, of course, we have to solve it numerically. So it's kind of the extrapolation between the free streaming and also the ideal hydro. Of course, for ideal hydro, it needs larger gamma head or the large system or dense system. So what we found interesting for this linear response actually it's not really sensitive to the transverse profile. Then I mean we need to, as I just mentioned, right? We need to make sure the hydrodynamic modes will dominate. Well, we have to make sure whether it's dominant or not. So then we just use that Q value. Then what we find is actually for gamma head smaller than 2, it's just the size R. If it's 2 times smaller than the mean free path, actually the particle like contribution dominates. Then if the R like 4 times larger than the mean free path, actually the hydrodynamic like contribution will dominate. Yeah, let's just summary what I said. So this gamma head, if smaller than 2, so then the particle like dominates. Then if larger than 4, so the hydrodynamic dominates. Then of course, I mean, if we have this theory in principle, we can compare to data in order to figure out what gamma head is. Then from this gamma head, we may say something in this theory about whether the contribution to flow is hydrodynamic or non-hydrodynamic modes. So what we find for central A collisions, of course, is standard conclusion. So actually hydrodynamic contribution dominates. But for this PA data, we actually find actually the non-hydrodynamic modes dominance. So then, I mean, there are also studies about attractor, as I just mentioned in bottom-up thermalization. So in the earlier time, so there's universal attractor behavior here. Of course, in this theory, so we also have early time attractors, and of course, there are also known late time attractors. Like actually, Paul also has a paper about that. Then, so this actually is intriguing. I mean, if we look at other theories at the earlier time, they will be different. I mean, kinetic theory, hydrodynamics, and the ADS-CFT, they will be different. Actually, they will dramatically different. Of course, we don't trust the hydrodynamic models for earlier time. But at least, I mean, if this part dominates, this actually distinguish all those theories for small systems. So in order to tell you more about this attractor, so for hydrodynamics, actually, we set up our initial conditions using this attractor solution, because, I mean, if somehow one starts from hydrodynamic models from earlier time, actually, you will end up with this attractor. So we just want to see then how different the kinetic theory and the hydrodynamic models will be different. And we actually found it quite different. So here, the solid lines are the kinetic theory results. We know, I mean, the hydrodynamic goals are the same in the theory, but obviously their flow will be different if both theory, one starts from the attractors. Of course, the attractors means in these two theories. I mean, the attractors are different in these two theories, actually. That's why it causes this difference. Then, I mean, we also calculate like a quadratic response in this theory. So this coefficient W just indicated by this formula. Then we also calculated the cubic response. It just is proportional to gamma height, is proportional to the E cubed. So E means the spatial anisotropy, spatial eccentricity. Then, I mean, we actually, at the end, we saw, I mean, all those results actually are the results for this complete theory. We didn't do linear response. So by solving this kinetic theory, actually, here I just show you some plots from the theory. So if we start from Trento initial condition, so actually in this event we have two peaks. Then if you do free streaming, actually these two peaks will separate at late time. But I mean, if you go to large gamma height, actually, or the large system or dense systems, actually all your matter seams will form one big drop of the QGP. I mean, of course, if go larger, this will be larger level. I mean, this peak will disappear further. So anyhow, I mean, that's basically what we have so far. So for large system, I mean, so I think most pictures seems consistent in bottom up. Of course, I mean, you can do more. You can do some field theory calculation, and so we need to solve these technical issues, to go beyond. Then for small systems, so actually it gives us the chance to study non-hydrodynamic modes in QGP. Then, so here I only show you the results for the interplay between hydro and non-hydrodynamic modes in this theory. But of course, at the end, we want to do the bottom-up thermalization. We know at some stage, if your transverse size is small enough, so this picture will be modified. Then eventually, of course, I want to do jet quenching like something. Well, we have started, I mean, for the factorization. But at the end, we'll put everything together, and I hope in the future I can tell you more. Okay, thank you.
Thank you, Bin, for this very interesting and big picture talk. It's like a really great finale to our meeting. It's an apt finale indeed. Thanks for putting this great effort for summarizing so much in such lucidly and such small time. So it's now time to take questions. Okay, so I have a question on your slide number 12.
Okay.
I think you were mentioning some non-renormalizability issue in the matching. I didn't completely get it. Could you elaborate on it?
So here, because I'm brief, I mean so I mean, if you do the classical simulation, so actually at the initial time, I mean, if you look at the vacuum distribution or the vacuum wave function, but in fields, actually you can include some. I mean, in the correlation function, you can include some one half the vacuum fluctuations. So let's just correspond to the vacuum fluctuations. I mean, for all the modes. I mean, if you look at harmonic oscillator, so you can see that. So you have like a n. I mean, the number operator plus one half. So actually, I mean, this of course for harmonic oscillator, but for field theory, for all the modes, you have this one half part. Let's correspond to the purely vacuum fluctuation, because if you put the n to 0, just if there's no particles, actually you have this one half in the vacuum. So that's the wave functions. If you include this in your wave functions, then you use this wave function for your initial fields. Starting from these fields, then you do some simulation. Actually, this one half will, if you do the simulation up to thermalization, of course, it's color dependent, but in principle, you can do that. You will find your thermal distribution goes like F equals P divided by T. I forgot it's minus or plus. I think it must be minus 1/2. So if you do the small p expansion for the Bose-Einstein distribution, you have P over T. I think maybe minus or plus 1/2, then plus some other terms corresponding to P to positive power. Then actually, I mean, if you don't include this vacuum 1/2, you only get the thermal phase point for your simulation only goes like, no, T divided by P, sorry. So your thermal field point goes like T divided by P. But if you at the initial time, you include the vacuum fluctuations, this 1/2 thing. So actually you will get T divided by P plus or minus this 1/2, right? So this
yes,
vacuum
but
fluctuation. So
I understand. Yeah, actually, I had a very conceptual question. If you look into the full quantum theory, there should be no issue of renormalizability. Is it because you're mixing quantum and some classical statistics together? And I think what is happening, because it seems a little bit surprising that there should be some, is it some technical issue or is it some?
It is some technical issue. I mean, in order to get, I think it's a little bit technical, but I mean, because here you need like a double time contour or Sabino Kaldish formalism. So you double the degree of freedom you feel. Then but in this contour, so you have field theory, but it just degree of freedom of your field theory is doubled. But this means the full quantum field theory. But if in order to get the classic simulation, you need to neglect some terms from this Lagrangian on this contour. So actually, after you neglect those terms, actually, you will end up with some theory with a new Lagrangian, which is approximation to the full Lagrangian. But this quantum field theory corresponds to this new Lagrangian is non-renormalizable. So this actually gives rise to the cutoff dependence of your numerical simulation. Because deeper down, you are solving a quantum field theory, but because you are missing some terms, you cannot cancel all the cutoff, all the UV cutoffs by introducing counter terms, at least not in this theory. Yeah, so let's, it's just non-renormalizability in quantum field theory, but in numerical simulations, you will see the effect. But the issue is how you can consistently do this cutoff dependence.
So I think what you're trying to say, if I get you right, is that the naive classical statistical theory may be wrong. You need some extra counter terms that comes from the original quantum picture and somehow, or
yeah, but those terms is actually is non-local. So actually we evaluated the counter terms.
Local terms, yeah, okay.
Yeah, it's really non-local. So it's just intrinsically non-renormalizable. So one needs to be careful. Yeah.
I see. Okay, thanks. So Kirill, would you have some question or comment on this? Or?
Yeah, it's basically a comment. It's just to add. I mean, I completely agree with what been said. So basically, the same reason why you have the Rayleigh-Jeans divergence in classical statistical theory. It's also the reason why you cannot just renormalize the classical statistical approximated theory when you have a quantum band half up to your lattice cutoff, basically. So it's a technical question. So if you neglect this quantum band half, then obviously you have neglected this quantum part. However, when you neglect the quantum band half, then there is no seed for plasma instabilities. If you don't neglect the quantum one half and get it up to your lattice cutoff, then you have the problem that, as been said, there are some counter terms that are just missing, and you have the problem that you cannot just renormalize it. So these are the two things one has to deal with. There are a few ways to avoid it, but you then break some other symmetries. So just as a comment. That's it's a technical difficulty, which I'm not sure if it has been completely solved.
Yeah, and then I have a question about to a later part of your talk where you talk about two different kinds of attractors in ADS-CFT versus this classical type attractor. So in the ADS-CFT attractor, the convergence happens at some time which is independent of the initial condition. Whereas I think in this other case, you have initial condition dependence, right? And so now what do you want to say, that after the convergence is happening, you have only hydrodynamics in the ADS CFT case, whereas in the case of the other case, you might still have, even after you approach the attractor, there'll be some dominance of non-hydro. What was the exact statement there?
No, I mean, in this kinetic theory, so you have attractor, so it's basically PL over PT goes to 0. So it's understandable. I mean, at the earlier time, because expansion dominates, the expanding effect goes like 1 over tau in kinetic theory, for example. It just means at earlier time, the expansion really strong. So you drive all the PL over PT to 0. Then, but I mean, in kinetic, in hydrodynamic equations, I mean, in this real student equation, if you go to earlier time, you also get attractor, but this ratio, PLO, PDO, PLO, epsilon, actually correspond to some negative value. So it just means, obviously it's not physical, right? But it is attractor, but it's not physical attractor in the earlier time in the theory. But in ADS-CFT, I'm not sure we can call it attractor because it does not correspond to some universal behavior. At the late time, of course, it's because it's approaching hydro or non-hydro, whatever you call it. But obviously at the late time, we have attractor in OV3 theory, we have this attractor. But at the earlier time, kinetic theory has some attractor, more or less you can say physical. But for this hydro, obviously it's non-physical. Yeah. So is this your question?
Yes, yes. Well, Paul would have a question now for you.
Okay, good.
Hi, this is Paul. So why would negative longitudinal pressure be unphysical?
No, I mean, because in Israel stud, so you need to introduce some additional term, right? In order to get rid of this non-causal something. But you need the underlying theory. Here we use the underlying theory for this hydro is the kinetic theory. But obviously, I mean, kinetic theory tells you differently. Right? So you do, at least for this, I mean, for this, if you can talk about class, the quasi-particle distribution, you should get 0. But obviously in these hydrodynamic equations, you get negative thing. That's what I mean by unphysical.
Yeah. I mean, Paul, in this case, we know the exact solution, right? And then this is a hydro approximation. So it might, I mean, it's you might argue with the boundary being that when PL goes negative, but we know it's going to break at early times, right?
So I'm confused now. I mean, on that slide here, we have an ADS CFT late time attractor that goes to negative PL at early times. And there's no issue with that. I mean, within kinetic theory, maybe that's unphysical, but I mean, kinetic theory itself is maybe not defined at early times either.
But the setup for their Israel-Stewart equations was underlying RTA kinetic theory, right?
Yeah, but I mean, you can adjust.
That's what I said.
Time things such that you get
I know,
presumably. So I am not sure what the statement is.
Well, let me say this way. I mean, so this part actually dominant by this term, right? I mean, so this mainly, I mean, it's dominated by non-hydrodynamic modes, but I mean, either SFT or you do the kinetic theory or, I mean, weakly coupling field theory, you don't get what you get from this real stud. But I mean, this attractor corresponds to non-equilibrium contribution, right? I mean, if we talk about this structure, it obviously is not come from the contribution from this part. Then
that's not obvious. That in Bjorken, that's not at all obvious. I mean, you do have an attractor in Israel hydro that comes from the hydrodynamic mode, even at early times.
Why?
But at early times, the Knudsen number is diverging, so you wouldn't trust this truncated linear expansion, would you?
Exactly. So you need to do the borrow sum or something like this.
So I mean, if you, I think it's your question is what is the true answer, right? I mean, if the true answer is kinetic theory, then okay. I mean, you have your answer. But if there is a sort of second order differential equation that's given by an Israel-Stewart class, then that has a hydrodynamic pole associated with it, and that exists at early times in Bjorken. It may not agree with your kinetic theory, but maybe your kinetic theory is not trustable at early times either. So it depends basically on what you think the right answer is. If you're a kinetic person and you say that kinetic theory is the truth, then I would agree with you. But I'm not sure that that's really the truth in something like a.
But we can also talk about ADS-CFT, right? You have to tell me what's the underlying theory for your hydrodynamic equations. Then if you get differently, of course, hydrodynamics is wrong because it does not correspond to the underlying theory. I mean, hydrodynamics is something, I mean, you need to put in something more or less, not really by hand, but it's kind of by hand, right? So it's not really come from the underlying theory for this, for example, for this term, right?
I'm not sure if I understand. In ADS-CFT, you also have a hydrodynamic pole. It exists also at early times in Bjorken. So I would claim that even in ADS-CFT, you have hydrodynamics in the sense that there is a hydropole that exists and dominates at early times.
That's true, but you have to, I mean, if whatever theory you take, right? Here we take kinetic theory, then you can also take ADS-CFT. Then we know, I mean, from both theory, we can derive kind of hydrodynamic equations, right? Then you just, if you believe any underlying theory for your hydrodynamic equations, then you have to make sure this earlier time attractor in your hydro is the same as your underlying theory. If they are differently, of course, I mean, you shouldn't trust this earlier time attractor in hydro. That's basically what we claim here.
But it could also be the other way around, right? I mean, it could be that you have a hydrodynamic description.
But where the underlying theory is
but
wrong.
You shouldn't trust whatever your approximation to your underlying theory is, right? I mean, if you could actually solve QCD at early times, I think we would all agree that that's the answer.
Yeah, okay.
Absent that possibility, I think it's an open question whether hydro is the thing that fails, or kinetic theory is the thing that fails, or ADS-CFT is the thing that fails. I think these are three different possibilities. Which one is the better approximation?
That's true. I don't disagree with you about it. But here, we just, of course, we start from kinetic theory. Kinetic theory, obviously, have something more than hydrodynamics here. I mean, at least in this weakly coupling limit. But I mean, the first treatment is why you say first treatment is wrong. I mean, the earlier trajectory in kinetic theory is first treatment more or less. I mean, of course, I mean, it will become non-zero at a finite time because of some interaction, but I mean, at least for the toggle zero limit, so that let's just first treatment.
No, I mean, I'm not disagreeing. I derive that, right? I mean, it's not that I'm disagreeing with that.
I think I understand with you. So you say, okay, if kinetic theory is wrong, so our argument is wrong. Of course, I don't, but you assume kinetic theory is wrong. Then we don't have to discuss about what we discussed. Because our starting point is because kinetic theory contains more. As long as you accept this quasi-particle picture, then obviously we find really different hydrodynamics we cannot really trust because this kinetic theory contains this hydrodynamics.
But Paul, I don't understand. I mean, the basic thing is that you start from kinetic theory, right? You know very well, you've written books on it, right? And you take the moments and you get some hydro equations, but we know the underlying theory in that case. So we can use that, you know, in some simple cases as a test, right, of different schemes, no? Now we can agree that, you know, this is not QCD and we can't make broad statements about QCD, but if we restrict our attention to simple RTA kinetic theory, then we know the answer, no? And then we use that exact solution to test hydro and not the other way around.
Yeah, I think I would agree with that. It's just that when it comes to interpreting, in particular, data and making statements whether PA is dominated by hydro or not, I think I would be very uneasy with sort of basing those conclusions on kinetic theory.
Well, yeah, that's why I emphasize is unit theory. Right? I mean, if you know the underlying theory, you can do the QCD calculation, of course, everything will be wonderful. We don't have to do any arguments. But for our study, we need to start from somewhere. Right? Here, we start from this quasi-particle picture of this kinetic theory. Right?
Yeah, so I actually have a related question then about this ADS CFT. Once you have this, once the thing converge on this attractor, is it hydro or there is still some presence of non-hydro? Is it a way to answer this question? Paul, could you make a comment perhaps?
Yes, once you're on the attractor, it's okay. I mean, what is hydro? It basically, the attractor is hydrodynamics in the late time limit, and it is.
Well, what I mean is actually it's this first order hydro or not. That's a very simple question.
Well, I mean,
whether it is first or
okay.
I mean it's just a normal diffusion pole, or is it like you have to resum many things?
Yes, I can answer the question. Just a moment. I'll tell you what the answer is. Let me see if I get this real quick. So basically, okay, yeah, I'll send a link and you can have a look at this, and maybe somebody else can ask a question or something.
Sure. Okay. So, any further questions or discussion you would like to bring up, or Bin, you would like to make any more comments?
I can make a comment here if desired. So I think, I mean, if we're really talking about small systems, right? I mean, and using, I mean, kinetic theory or whatever, right? I mean, I think one of the things that, you know, we're commonly forgetting in these discussions also is that, you know, a lot of the tools that we use are kind of ensemble averaged on very small scales, right? And it's, I mean, if you just think of like what's the Compton wavelength of a quasi-particle or so in comparison to the system size, right? I mean, then we may be kind of violating a bunch of important principles and kind of pushing these things to such small scales. So, I mean, of course, that's hard to address theoretically, but, you know, it's just something, I guess, to also keep in mind, you know, when we really make statements there. So it's more of a comment.
Yeah, I don't disagree. I mean, of course, I mean, in reality, we can do, but you just, I mean, technically how we really accomplish it. I mean, there's a lot of things to think about it.
Okay, Paul has this reference where he essentially, I think it is first order hydro once it converge on that attractor, you know? That's the figure 1 tells us more. First or second. Okay, good.
Yeah, and the rate at which it approaches the attractor tells you information about the quasi-normal modes in the case of ADS, right? So that the rate at which it approaches will tell you information about the non-hydro modes.
I think not the rate, I think it's the exact time, that the time at which it converges on the attractor itself is an indicator of the quasi-normal mode. I think so. And the rate also, of course, I mean, because, yeah. Yes, indeed, yeah. Okay, so in that case, let us thank Bin again for this very grand finale talk. And thanks to all of you